Okay, I think we'll get started. So today we're going to start the first of 3 lectures dealing with the laws of thermodynamics. So we're going to step through these laws still at the level of this of our introductory course here. We'll certainly come back to these in more rigorous fashion in the higher courses in this curriculum. But we want to start getting some of these ideas down and understanding what thermodynamics is talking about. Along the way, we'll pick up some other ideas that come in. In this particular case, we're going to pick up heat capacity, the heat capacity equation, and how to do some calculations there. All right, so the first point here is that contrary to sort of everyday speak, temperature is not heat. We'd say, oh, it's hot outside or it's cold outside. But temperature is certainly related to heat, and it's related through something called the heat capacity equation. Which is Q, heat, equals C delta T. And so how do we interpret heat capacity? This is the heat capacity here. So we look at this equation. If we want to make a temperature change of a certain amount, if our heat capacity is large, then we're going to need more heat energy to do that. If our heat capacity is small, we're going to need less heat energy to do that. And so the heat capacity is the capacity for the system to resist a temperature change. So it requires more energy to cause the same temperature change, let's say 1 degree Celsius or 1 degree Kelvin. Now, heat capacity itself is an extensive property. So we talked about intensive and extensive properties. And if we were to, say, cut a block of iron in half, it would take half the energy to heat that smaller block than the larger block. So heat capacity is an extensive property. But we will often want to work with intensive properties, as we've talked about. So the 2 common ones are the molar heat capacity, Cm, and this is the heat capacity divided by the number of moles. And then we have heat capacity divided by mass. Usually when things are divided by mass, they're called specific. So specific heat capacity. And honestly, I'm not sure where that word specific came from historically, but if you make an intensive property by dividing by mass, it's often called specific. All right. Now, there is more to heat capacity, and as we go up into a more advanced thermodynamics course, we will see that heat capacity is not constant. But for our purposes, at normal laboratory conditions, under reasonable temperature changes, heat capacity is essentially constant. So around room temperature, heat capacity is a very, very weak function of temperature. And so we take it to be constant. It does matter the conditions under which you measure heat capacity, and we'll talk about this when we get to gases. It's more pronounced with gases. So it does matter if we're heating something at constant pressure versus heating something at constant volume. But we'll defer that discussion for a while. Let's do a quick example. Largely, I'm going to just let you be on your own with these. I think that if you look at both your physics book and your chemistry book, you'll find plenty of problems that help you get the heat capacity equation down. It's pretty straightforward, so I think you'll be fine with that. We'll just do one example here. So let's say it takes 100 joules to heat 10 grams of iron such that its temperature changes by 22.3 degrees Celsius. And Celsius is the SI unit for relative temperature. We have Kelvin, which is the SI unit for absolute temperature. So temperature is interesting in that there is an absolute zero of temperature. This is unlike energy, where energy is always on a relative scale. We can say there is a temperature below which we can't go. So there's an absolute temperature. If we call that 0, then we develop a temperature scale that's called an absolute temperature scale. If we call something else 0, for the case of Celsius, it's when water freezes. So it's relative to the freezing point of water. It's based off the freezing point of water. Then we call it a relative temperature scale. If you're in the non-SI system, so here in the United States, we typically use Fahrenheit for the relative temperature, and the absolute temperature associated with Fahrenheit is called Rankine. So the Rankine scale starts with absolute 0 of 0 Rankine. But for the case of Celsius and Kelvin, a change in 1 degree is the same. So a 1 degree Kelvin change is a 1 degree Celsius change. And in the Fahrenheit system, a 1 degree Fahrenheit change is a 1 degree Rankine change. All right, so whenever we're working with delta T's, we can use Kelvin or Celsius interchangeably. But whenever you're working with the absolute temperature, then you want to make sure that you're using Kelvin. All right, so let's express this now as Q equals M times the specific heat capacity. So that's what we're going to try to calculate here. We know the mass, we know the temperature change, we know the heat. Let's calculate the specific heat capacity. So we can set 100 equals C times 22. This should be an arrow. And we just solve this and we get 0.449 joules. So that's the energy unit per gram per Kelvin. So it's usually in Kelvin here. You could put per Celsius. That would be fine too. So there's our answer. Let's get the molar heat capacity. So the atomic weight of iron is 55.845 grams per mole. So if we take the specific heat capacity and multiply by the atomic weight, we get our grams to cancel. And we're left with joules per Kelvin mole. So we get 25.07 joules per Kelvin mole for the molar heat capacity of iron. All right, so this is an example of the typical calculations. So find some of those in your book, and I think you'll get on top of this really quickly. All right, let's get into more of the meat of the lecture here, laying down our first law of thermodynamics, which is the Zeroth Law, so that can be a little confusing. So the first one we run into is something called the Zeroth Law. And we need a little bit of a definition first, and that's this idea of thermal equilibrium. So if we take a system A and a system B, and we connect them via a perfectly conducting wall. This is sometimes referred to as a diathermic wall. So it's the opposite of the adiabatic stuff we've been talking about earlier, where you have an insulated wall. Here it's perfectly conducting, so heat can flow perfectly freely through the wall. Thermal equilibrium is defined that when you connect these two via a perfectly conducting wall and you observe that no heat flows, okay, that defines thermal equilibrium, and we say that the temperature of system A is equal to the temperature of system B. Temperature will tell us the direction of heat flow. So if we are not in thermal equilibrium and we attach these and we see a net heat flow from A to B, then we say the temperature of A is greater than the temperature of B. So heat will flow down a temperature gradient or a temperature difference. And it will do so until the system reaches thermal equilibrium, if nothing else is going on there to maintain that temperature difference. Okay, so that's thermal equilibrium. Now, why do we need the Zeroth Law? Why is it called the Zeroth Law? It's sometimes not even listed, and you won't find it, I'm pretty sure you won't find it in your Gen Chem book or in your physics book, they'll just start with the first law. And that's because this is seemingly so self-evident. The reason is that as we get more advanced in our studies here, we will discover that thermodynamics is an extremely rigorous theory. So everything is done very carefully and mathematically, and this is essentially a very careful mathematical statement that helps maintain that rigor in thermodynamics. And so it says that if system A is in thermal equilibrium with system B, so what does that mean? It means we're going to put A and B together and no heat will flow. And system B is in thermal equilibrium with system C. So that means C and B are touching with a perfect wall and no heat is flowing. Then system A and system C are in thermal equilibrium, which might seem obvious, but the key point here is that A and C are not touching via a wall. They're separated. And so what this law does for us, it allows us to rigorously extend the concept of thermal equilibrium without having to contact and measure if heat flows or not. The mathematical statement of the Zeroth law is this. And if you've had a little bit of algebra or some formal sort of math theory training, you would recognize this as the property of transitivity. So if TA equals TB and TB equals TC, what is this saying? This is saying thermal equilibrium, then TA and is equal to TC. So thermal equilibrium is a transitive property. Now, one of the most immediate ramifications of this is something really important, and that is the idea of a thermometer. So this allows us to rigorously produce this thermometer. Now, here we're talking about sort of the theoretical concept of a thermometer, but let's draw this with pictures of a thermometer we're familiar with, a physical thermometer. So in this case, the thermometer is going to be system B. System A, we put the thermometer in system A and B, and the thermometer is usually very low in mass, so it won't impact whatever it comes in with its temperature, it won't impact system A. And so in the limit of sort of this thought experiment or thought idea or theoretical thermometer, we say that we can put this into the system without influencing system A. This will respond with some measurable physical property. So if it's mercury in a glass capillary tube, mercury will expand if it's heated, and it will contract if it's cooled. So that will move up and down this capillary. And so there's some kind of physical measurement we can make and associate that with the thermometer when it is in thermal equilibrium with system A. Then we can put the thermometer in system B, and if the physical response of that thermometer is identical, then we say system B and system C are in thermal equilibrium. And if these were the same reading on that thermometer, then we would say system A and system C are in thermal equilibrium. Okay, well, this feels a little limited because these have to be the same at this point. But what we can do now is calibrate this and then put a gradient scale on that thermometer, and then it becomes what we are familiar with for a thermometer. So let's choose a system here where we have, say, ice. So this would be the Celsius system. And so temperature is equal to 0, so the freezing point of pure water. We put in our thermometer and we read the mercury or alcohol or whatever the thermometer is made out of to be at that position. Then, not expecting thermal equilibrium, we put it into another boiling water And here is the second point in this 2-point calibration scale, and that is 100 degrees Celsius. And so that marks right here. And so we expect a physical change in the system of the thermometer. If it doesn't change, it's not a very good thermometer. So we now have these two marks coming from our calibration. And then we can just put a gradient scale, interpolate between these two. We can extrapolate beyond, and we have ourselves a thermometer such that if we now put this into some just unknown system, and we end up right here, say, oh, this system would be in equilibrium with a system that is at, say, 75 degrees Celsius, whatever we read from the thermometer. And so while this law seems kind of silly, and the idea of a thermometer seems so obvious, the reason it's there is for the rigorous development of thermodynamics. And thermodynamics is really our most well-established theory. Anything we say must be true or must be false in thermodynamics, particularly equilibrium thermodynamics is what we'll be talking about. Then it is definitely true or false in as much as we are confident in things such as conservation of energy. So thermodynamics rests on some really, really well-established physical laws, which we'll be writing down here in the next couple of days. And from that grows then through just pure logic and mathematical manipulation, the ability to calculate all sorts of different relationships that are not as obvious as things like this. All right, so again, practice problems with the heat capacity. Make sure you're really good at that. And then just tell yourself the story of this. There's not a lot of homework problems we can have per se, but start to think about, okay, we're laying down the ideas of thermodynamics. Here's the law. This is a consequence of the law.